Assalamualaikum, my name is Farah Farhana Binti Mohd Harun, matric number S72564. Today I'm going to present the individual assignment for subject Planktonology MMB3323. Do you know iron compound? What do you think would happen if we dump the iron into the ocean? Would it create a toxic environment that kills all the fish, or could it actually help us mitigate climate change? Today we are going to explore a surprising role of iron in our ocean and how this simple element could be a powerful tool in the fight against global warming. So, what really happens when iron is added to the ocean? This method is called as ocean ion fertilization. It is where the iron is intentionally added to the iron-limited, high nutrient and low chlorophyll region of the ocean to stimulate phytoplankton growth. This process enhances biological pump that captures atmospheric carbon dioxide through photosynthesis and subsequent sinking of organic matter. How did scientists come up with the idea of using iron to help the ocean absorb carbon? It began with the discovery of ancient atmospheric carbon dioxide levels. By analyzing ice cores from Antarctica and the Arctic, scientists found that during the last glacial maximum, carbon dioxide levels were around 180 ppm, compared to approximately 280 ppm in the pre-industrial era. The significant difference in carbon dioxide levels raised an important question: what caused this change? That's where John Martin comes in. He proposed that during the glacial period, higher dust levels containing iron were deposited into the ocean. This iron stimulated phytoplankton growth, particularly in high nutrient, low chlorophyll regions like the Southern Ocean, enhancing the ocean's ability to absorb carbon dioxide. His idea laid the foundation for what we now call ocean ion fertilization. John Martin's hypothesis sparked interest in how we could use this natural process to our advantage. This brings us to the main objective of ocean ion fertilization, to enhance the growth of phytoplankton in certain parts of the ocean by adding iron with the goal of increasing carbon dioxide absorption from the atmosphere. By stimulating phytoplankton blooms, OIF helps boost the ocean's biological pump, which draws carbon from the surface to the deep sea, where it can be stored for long periods of time. In short, the objective is simple: use iron to support nature's ability to fight climate change. Ocean ion fertilization is most effective in specific regions known as high nutrient, low chlorophyll areas or HNLC zones. These areas have plenty of nutrients like nitrate and phosphate, but they lack enough iron to support large phytoplankton blooms. By adding iron, we can unlock the potential of these waters to absorb more carbon dioxide. Some of the key HNLC regions where OIF has been studied include the Southern Ocean, the Equatorial Pacific, and the North Pacific. These zones are considered ideal for OIF experiments because a small addition of iron can lead to a big impact on phytoplankton growth and carbon uptake. So, why are these HNLC areas chosen? First, they have plenty of nutrients but very little phytoplankton, and that's mainly due to a lack of iron. Next, scientists study these areas to understand how iron limits phytoplankton growth and how that affects marine food webs and carbon cycling. Also, these regions are thought to have high carbon drawdown potential, making them important for evaluating how effective ocean ion fertilization could be in mitigating climate change. The idea of ocean ion fertilization all started from John Martin's famous hypothesis back in 1990. From 1993 to 2009, a total of 13 artificial ocean ion fertilization experiments were conducted in different HNLC regions. The first OIF experiments was conducted in 1993, which is the IONEX one, but the result obtained was weak. So, in 1995, IONEX 2 were conducted, and it repeated the same experiment at the same area and gained a better result. In 1999, another experiment was conducted, which is Southern Ocean Iron Release Experiment. It is the first experiment conducted in the Southern Ocean. The following year, which is in the year 2000, the next experiment was conducted, which is S72564. Next, in 2001, Another experiment was conducted, which is SEEDS-1. In 2002, there are multiple experiments was conducted, which is SOFX-S, SOFX-N, and series. In 2004, there are several experiments conducted. The first one is the IFAX, second one is SAGE, and the third one is SEEDS-2. IFAX is the only one that was considered truly successful in demonstrating significant carbon export to the deep ocean, which is the key goal of OIF. Next, in 2005, FEEP was conducted. In 2009, LOHAFAX also conducted. Both of these experiments was conducted in Southern Ocean. So, why did only one experiment show successful carbon export? There are several key challenges that limited the effectiveness of the others. First, the presence of other essential nutrients plays a big role. Iron alone is not always enough. If other nutrients like silica is lacking, phytoplankton growth won't last. Second, the ecosystem response matters. Zooplankton grazing can quickly consume the phytoplankton, and changes in species composition can affect how much carbon actually sinks. Third, the short duration of these experiments made it difficult to measure long-term effects. We don't know how much carbon was really stored or how the ecosystem changed over time. And finally, there is the issue of rapid iron dissipation. Iron tends to spread out or sink quickly, so the phytoplankton bloom might not last long as enough to make a significant impact on carbon export. These factors show that while the concept of OIF is promising, it is also complex and not as straightforward as it might seem. So, what does the future of ocean iron fertilization look like? To truly understand its potential, scientists believe a few major improvements are needed. First, we need extended duration studies lasting 3 to 5 years to see whether the effects of iron addition like carbon export are sustained over time. Second, we need more comprehensive monitoring. This means using advanced tools and systems to carefully track ecosystem responses, phytoplankton activity, and carbon movement through the ocean. Third, there is a growing need for international collaboration. By sharing data, standardizing methods, and aligning efforts with global climate goals, we can make research more effective and impactful. And finally, any future OIF projects must include environmental impact assessments. These should look at potential risks to marine life and changes in biogeochemical cycles to ensure that OIF is safe and sustainable. With these steps, OIF could become a more reliable tool in the global strategy to combat climate change. That brings us to the end of my presentation. I hope my sharing has been helpful and given you a better understanding of ocean iron fertilization and its role in addressing climate change. That's all from me. Thank you.